Good morning. In this lecture, we are going to cover AC machines. In AC machines, we are going to see the working principle, construction and speed control of an induction motor and working principle and construction of a synchronous motor. The first one is induction motor. The induction motor is also called as asynchronous motor, which means the motor will not rotate at a synchronous speed. The expression for a synchronous speed is ns equal to 120 F by P. Moving on to the content of an induction motor. First, we are going to see the construction of an induction motor. The constructional parts of an induction motor are classified into two types. The first one is a stator and the second one is a rotor. Stator is a section which does not rotate and a rotor is a section which rotates. The rotor construction can be of two types. The first one is a squirrel cage rotor and the second one is a slip ring rotor. Each one has its own advantages and disadvantages we are going to see in the constructional section. Moving on, next we saw the working principle of an induction motor. In this working principle of an induction motor, and we are going to see how the induction motor starts. And next we are going to see the expression synchronous speed. The expression for a synchronous speed is equal to 120 F by P, where F is the frequency of a supply, P is the number of poles. And moving on, we saw the expression for slip speed, percentile slip. And next we saw the expression for a torque produced by an induction motor, and we also saw how torque is getting affected with a change in other parameters. Especially we are going to see how torque varies with a change in slip. And final concept is speed control of induction motor. There are different speed control methods available to control the speed of an induction motor, but we mainly focused on these three speed control methods as these three are most widely used. The first one is a pole change method. Here we are going to change the number of poles in a stator and control the speed of the motor. In a stator voltage control method, we are going to change the applied voltage to the stator and control the speed of the motor. And in V by F method, we are going to change both voltage and frequency applied to the stator and control the speed of the motor. Moving on, our next machine in AC machines is synchronous generator. In synchronous generator section, first thing we are going to see is the construction of a synchronous generator similar to that of an induction motor. The construction of constructional parts in a synchronous generators are also classified into two, which is a stator and a rotor. Stator does not rotate, rotor rotates. Rotor construction can be of two types. The first one is the salient pole type and second one is a smooth cylinder type. Each one has its own advantages and disadvantages. Moving on, next we saw RMF, which means a rotating magnetic field. In this section, we are going to see how we are going to generate a rotating magnetic field with the help of a three-phase supply which are placed on the state. These three stator windings are placed with 120 degrees apart physically and electrically. And finally, we saw the working principle of a synchronous generator. Next, losses in machine. These losses are common for a DC machine. It can be of either a generator or a motor or induction motor and a synchronous generator. All these losses are present in any moving electrical machine. Now coming to the losses. The losses which are present are classified into two. The first one is electrical losses and the second one is mechanical losses. Electrical losses are again classified into core losses, copper losses. Core losses are the losses which occur in the core or iron is called as a core losses. Generally, these type of losses occur in stator core or a rotor core of a machine. Machine can be of either a generator or a motor, whereas copper losses occur in the copper, which means in the winding of the armature or a stator. Core losses can again be classified into two types. The first one is a hysteresis losses and the second one is eddy current losses. We discussed what are hysteresis losses and what are eddy current losses in the transformer section. You can write the exact same explanation. If you recollect, hysteresis losses can be mitigated or reduced by adding silicon to the steel, whereas eddy current losses can be reduced by laminating the core. Moving on to the mechanical losses. Mechanical losses are again classified into two types: frictional losses and windage losses. These frictional losses are due to the friction in the bearings, and windage losses are due to the friction or air resistance by the wind onto the armature or a rotor. Induction motor. Induction motor is also called as asynchronous motor, which always rotates less than the synchronous speed. We know the expression, and we also know what is the synchronous speed, which is ns equal to 120 f by p, where f is the frequency and p is the number of poles. If you substitute the frequency value and number of poles present in an induction motor onto that particular equation, you will get a synchronous speed, which means the stator field, which is nothing but a RMF, rotates at synchronous speed. Generally, for an induction motor, the induction motor never rotates at a synchronous speed at which the RMF rotates, so it is called as an asynchronous motor. The induction motor speed is always less than synchronous speed, so NR is less than NS. And the working principle of an induction motor is mutual induction. If you recollect, the working principle of a transformer is also a mutual induction. So induction motor can also be called as a rotating transformer. And induction motor can be classified into two types. The first one is a single phase induction motor and the three phase induction motor. Single phase induction motor is not in your syllabus. We are going to concentrate only on three phase induction motor. Three phase induction motor construction. As we discussed in the introduction part, the constructional part of a three phase induction motor or single phase induction motor can be classified into two types. The first one is a stator and the next one is a rotor. If you observe the diagram, if you look into the diagram, this section is called as a stator. This section is called as a stator. On the stator, we have a yoke, the outermost part, which we can touch. Inside, we have a stator core, generally made up of laminated steel. In the stator core, there are windings present. Generally, a three-phase winding is present. These windings are generally made up of copper. Moving on to the rotor construction can be of two types. The first one is a squirrel cage rotor and the next one is a slip ring rotor. In the squirrel cage rotor, there will be two end rings and inside there are rods. These end rings are connected with the help of the rods. Internally, this is the circuit diagram. These are the end rings and these are the rods. These rods are also called as rotor conductors or rotor parts. They are generally made up of aluminum or copper and the end rings are generally made up of copper. Now moving on to the advantages of this type of construction is that as everything is welded together, this type of a structure is a most rigid structure. So for this type of rotor, less maintenance is required. Due to this advantage, most of the machines used in industries are squirrel gauge induction motors, and the application where this type of rotors are used is at a drilling machines, printing machine, lathe machines, etc. Moving on to the second type, which is a slip ring induction motor. For this particular induction motor, we have a slip ring type rotor. If you observe, there are two discs. They are called as a slip rings. Over that, the pressures will. Moving on to the internal construction. Internally, there will be a three-phase winding similar to that of a stator winding, and there will be also a core inside the rotor. The advantages of slip ring type rotor is this type of rotor generally has high starting torque, and there is a possibility for rotor resistance speed control method, which means we can control the speed of the motor by changing the resistance of the rotor, whereas in the previous case, in a squirrel cage type of rotor, as it is a one rigid structure, no terminals are present, we cannot connect or add resistance in series with the rotor bars. So rotor resistance speed control is not possible with this type of squirrel cage induction motor, whereas here the terminals are available, a separate RYB terminals are available. We can add additional resistance in series with the rotor winding and control the speed of the motor. And this type of slip ring type rotor is used in applications like elevators, cranes, lifts, and we also saw the slip formula for a slip. S is equal to ns minus nr by ns, and percentile slip equal to ns minus nr by ns into 100%. And this is a little comparison table for a slip ring rotor type and squirrel gauge rotor type induction motor. Moving on to the working principle of induction motor. Now, if you observe, this section is a rotor, the upper section is a stator. As a stator is connected to a three-phase supply, and three-phase winding is connected. Three-phase winding is present in the stator, and RMF, rotating magnetic field, is produced. As a stator produces a rotating magnetic field, suppose let at a particular instant, here it is a south pole and here it is a north pole. Flux lines will flow from north pole to south pole. As this flux is a rotating flux which is flowing in a clockwise direction, we have a relative motion with the conductor. So applying Fleming's left hand rule, index finger indicates the direction of flux, thumb indicates the direction of a motion which is in the clockwise direction or towards right of your screen, and middle finger indicates the current induced. So if you apply Fleming's left hand rule in a rotor conductor, the current induced will be inside the screen, which will be a cross. Next, moving on, if you observe, a conductor in a rotor is carrying a current which is into the screen. If you apply right hand grip rule to that conductor, to apply right hand grip rule, you have to place your thumb in the direction of a current which is into the screen, and your four fingers indicates the direction of flux produced around the conductor. So as applied right hand grip rule, the direction of flux produced around the conductor will be in a clockwise direction. So if you observe, to the left hand side of a rotor, we have a flux going upward, and to the right side of the rotor, the induced flux is downward. So to the right, these flux whichever be induced will support that and increase the density of flux in this section, whereas to the right of the conductor, as the induced flux and the already existing flux due to rotating magnetic field opposes each other, the resultant flux will be less to the right of the conductor. So the final diagram will be a more number of flux lines are present to the left of the conductor and less number of flux lines are present to the right of the conductor. As there is imbalance in the flux, the conductor will try to move from higher flux region to a lower flux. So the conductor moves in a clockwise direction. In this way, the induction motor will rotate. So our next concept is speed control of three-phase induction motor. There are different speed control methods to control speed of an induction motor. The most commonly used type of methods are, the first one is a pole change method. Here we are going to change the number of poles and we will vary the speed of a motor. The next one is a stator voltage control method, and the final one is V by F method, or a variable voltage and variable frequency method. The first one, pole change method. As we know the expression Ns equal to 120 F by P, which means the synchronous speed is inversely proportional to the number of poles. So as we add the number of poles, increase the number of poles, the synchronous speed varies. As the synchronous speed varies, the rotor speed also varies. In this way, we are going to control the speed of the motor by changing or adding the number of poles. So problem with this type of speed control method is we need additional windings in order to add extra number of poles. So a special type of stator construction is needed for this type of speed control method. Moving on to the second type, which is a stator voltage control method. As we know the expression for a torque, which is equation 1, and if you observe from this equation 1, the slip is inversely proportional to EMF. So by simply changing the applied EMF, we can change the slip. If a slip changes, the speed of the motor will change. The next one is variable voltage variable frequency method, or V by F method, or also called as flux control method. In this type of a method, we are going to change the such that the ratio of V by F is constant. So if you observe the torque expression, if we reduce the V by F ratio, the torque of a motor reduces. If a torque reduces, the speed of the motor can be varied. In this way, by varying the ratio of V by F, we can vary the speed of the induction motor. So next concept is a synchronous generator. A synchronous generator is a machine which runs at a synchronous speed, which generates a three-phase AC supply. Synchronous generators are also called as alternators. Moving on to the next concept, construction of synchronous generator. Any machine will have two major parts. The first one is a rotor and the second one is a stator. The stator construction of a synchronous generator is similar to that of a stator construction of induction motor. The stator has only one type of a construction where three windings R, Y, B are placed at 120 degrees apart. Moving on to the rotor has two types of construction. The first one is a salient or a projected pole type. You can observe a projected poles are present on north and south pole, and over these poles the windings are wound as north and south poles are electromagnets. And the next type of a construction is smooth cylinder or non-salient pole. Here, instead of a projected pole, a cylindrical type of rotor is chosen and a winding is wound over that cylindrical type of rotor, such that this section is a north and this section is a south one. And a comparison is drawn between a salient pole and non-salient pole. A salient pole contains a projected pole, whereas a non-salient pole contains cylindrical poles. Here it has a non-uniform air gap between a rotor and stator. whereas here it has a uniform air gap between the rotor and stator. And the next one is axial length of a rotor is less. Here the axial length of a rotor is high. It is mainly used for low and medium speed alternators, whereas non-silent pole type rotor is used for high speed applications. The rating of alternator is very less, whereas in a non-silent pole the rating of alternator is more. Next, working principle of synchronous generator. As this is a generator, the working principle is Faraday's laws of electromagnetic induction. If you observe, as three-phase supply is given to the stator, a rotating magnetic field is produced in the stator, and with the help of external excitation, we are going to lock the north pole and south pole with the rotating magnetic field such that slip becomes zero. Generally, this type of locking is done by a DC motor. In conclusion, first read construction and working of an induction motor. Construction and working of an any machine is most important. First read that one. And moving on, you can expect a short answer question from this section. And next read the torque equation, and next speed control of induction motor. In synchronous motor, first read the construction and then working of an asynchronous motor, and finally go to the RMF, which is a rotating magnetic field.